Hi, this is Father Eckstedt, and this instructional video has to do with section 1.2. I'm making it because we lost a class on Friday because of the fire alarm fiasco. And I hope to keep this relatively short and quick, but it's what we'll need for section 1.2. These instructional videos are can be a nice supplement from time to time as we need them. They allow me to do such things as drag in the calculator should we need it to make a calculation, or if we need the textbook, bring the textbook in. And of course, we can look at the notebook presentation that I had ready for class. So let's be about that, and let's begin by looking at the quiz. And just to start from the top, remember number 1, we're looking for the x's, the x values, where these two functions equal. And they're always going to equal whenever they intersect or cross. And the x values that we're interested in are at -2 and 2. So there's a lot going on in that diagram. Look at it carefully. Notice that we're asking about the values of x, not the values of y. Question 2, we're told we have an even function, and by definition, an even function happens when the sign of the input, the sign of the x, doesn't matter. And therefore, if it's an even function and we know we have 9, 7 on the graph, then there must be a point on this even function at -9, 7, because once again, the sign of the x doesn't matter. So 9 gives off 7, as does -9. Question 3 there at the bottom, we're asked about the domain, and one way of thinking about the domain issue is, what can x be? And because we have an even radical, a square root, we cannot have a negative value under an even radical. And so the last thing, or you might say the first thing that we could have, would be 0 itself. And 0 would occur when x is 5/2, because 5/2 times 2 is 5, and 5 minus 5 is 0. So the smallest value in the domain must be 5/2. Anything smaller than 5/2 will create a negative under the radical sign. Going on to question 4. Question 4 is asking about the smallest value in the range, and there are 2 terms. And so we need to think about what's going to happen when we put the smallest value in for each of the terms. So it seems to me that you can never get anything less than 0 when the absolute value is involved. And so the first term, 2x, when x is 0, you're going to get 0 out. And the second term, it'll be at its smallest when you put in -3/2 for x. Because once again, taking the absolute value of -3/2 times 2, which is -3, adding 3, gives you 0. And the square root, the absolute value of 0 is 0. So in this particular case, now we test in the function itself those 2 values, 0 and -3/2, and both of them give off a value of 3. And so the smallest value that this function f of x will ever give is 3. This is the most difficult, challenging question that we had on the quiz. Number 5 is a piecewise function. And again, we're looking for the range or the set of answers, maybe best thought of as what are the y's. And the easiest way to tell with functions is to think about their graphs. And so this one has a piece of a parabola that is until x comes up to 2. And so this parabola, I got the portion of it drawn here at the right. The parabola goes through the origin, comes down to -4 when 2 goes in, and then it would begin to bounce back, but remember x can't be more than 2. The other piece of this function is the absolute value of the quantity x minus 4, and this function gets to 0 when you put 4 itself in, and then it looks like an arrow either side, but it keeps going to the right but stops abruptly at 2 when going off to the left. And then evaluating the picture, you can see that the y's get as small as -4, that is the range values, and then they can get as big as you want as it goes up. The sixth question is perhaps the easiest question. Which ones are functions? Use the vertical line test. Remember the vertical line test, it can only cross the function once. And so numbers or Roman numerals 1 and 2 and 4 would all pass the vertical line test. Roman numeral 3 and Roman numeral 5, they would both fail the vertical line test because we can draw vertical lines that touch the function in more than one point. So that was the quiz. Everybody got full credit for the quiz that was present. We didn't have time for the quiz because of the fire drill. So let's take a look now at section 1.2. And in section 1.2, we're just going to look at a number of different kinds of functions. We won't look at all possible functions, just some that are essential. So we're going to do this because these functions can model relationships that are observed in the real world, and mathematical models never can do this completely accurately, but we want to have a model that's good enough so that we can use it to perhaps predict the future or arrive at some conclusion about the relationship between two or more variables. So, first kind of function we're going to look at is the most widely used and the simplest, and that is the linear function. And I mentioned in class, I think on the first day, that the difference between y equals and f of x equals is the fact that whenever we use the functional notation, that is f of x, we're guaranteed that we're looking at a function. We don't have to test it. And so whenever the book says f of x, g of x, h of x, those are functions. They pass the vertical line test. So you may recall your favorite look for a linear function, y equals mx plus b. And I've taken the m out and the b out, and I've replaced them with 1/2 and -2, and looked at a very particular linear function as plotted on the plane at the left. The y-intercept is -2, that's what the b is, and the slope is, using those intercepts, we can see that from the y-intercept we needed to go up 2 and over 4, and rise over run, or up 2 over 4, means we've got a slope of +1/2. And lines can be displayed in several forms. Here are 5 of the most widely used. I put slope-intercept in the middle. Some more basic or typical forms are the general form, which is always set equal to 0. Standard form, we always put the constant, that is, the number that's not associated with either variable, the coefficients. We put the constant by itself over on the right. The point-slope form is used when we know one point and the slope, and it's one of my favorites. So I bring your attention to it. Seems I can't use my pen. No, not yet. So let me take a second and fix. So this slope-intercept form, I have it here in the middle, but there are other types. The general form is always set equal to 0. Notice if you put any of these points in, the general form would be true. The standard form is very much like the general form, but we just take the constant over to the right side. Point-slope form, we'll be using this a lot, and if you're not familiar, well, you'll catch up to things. I sort of like this intercept form. We're used to the y-intercept, which is -2. The x-intercept is often labeled a, and so a and b in the denominators. X over its intercept, which is 4, y over its intercept is -2. Set it equal to 1 and you're done. The intercept form is a nice linear form. There are others, but these are the ones that we'll be using periodically throughout the course. We talk about polynomial forms. Here's the form of a polynomial function. Here's a great example here of a polynomial function. It's of degree 6, we say, because its highest power of x is 6. Notice that it doesn't have to have every single power of x. One or more may be missing. So in this one, there's no x to the 5th term or x term or x squared term. It has a constant of radical 2 at the end. Doesn't have to have 1, could be 0. So that's just an example of one possible polynomial function. And in the book, these are a little small, but you'll see them in the book. Here's a cubic function, has that, cubic, has that characteristic cubic shape, sort of like a sideways S. And here's what's called a quartic function, or 4th degree polynomial, has that characteristic W shape. And here's what's called a quintic. I like quintics. I call this the Loch Ness shape, like the Loch Ness monster, right? And also with these polynomial functions, they take the opportunity to talk about something from physics. In this case, we've got a ball that's dropped from the CN Tower. And of course, we're in Canada, so it's measured in meters, about 1,600 feet tall. And its height from the ground is recorded at 1-second intervals. That's the data that's in the table. And then that data is plotted. And you can see it's not in a linear form, it's a curve. And so one of the things we'll be doing very soon is taking data such as this and fitting a curve to it. So this curve, this 2nd degree polynomial curve, it's data that looks like part of a parabola. And notice how well it fits. And we'll be doing such things in the not too distant future. The next thing we're going to look at are what are called power functions, and in this case, the power is a constant. And so we have 5 types here. X to the 1st, the 1 is, if it's not there, it's understood. This is what we call a linear function. That's a type of power function. Here's a quadratic. Y equals x squared, has that characteristic parabola shape. Y equals x cubed, right, that sideways S shape that we just talked about. X to the 4th, a quartic, x to the 5th, a quintic. These are 5 very specific power functions. Notice in every case the variable is the base. And in each case, what's constant is the power. These are called power functions. Make sure that you understand the difference between power functions and exponential functions. Notice now the variable is in the exponent. I like to say that x is in the exponent with exponentials. X in the exponent. So here's two sketches, one with the base is 2, and the variable is now in the exponent, right? And you get this characteristic exponential shape where things start small and then they take off very quickly, right? And if that base is a number between 0 and 1, such as a half, you'll get an exponential curve, but this time it'll decrease very quickly and come at 0, right? And never quite get to 0. So we'll be looking at those exponential functions as we go in the course. We'll spend some time with log functions. Log base 10 or common logs, if you pulled out your calculator and there is a common log key, a log base 10 key, if you turn that calculator on and put 1 in, for example, the log base 10 of 1 is 0, and you can see that clearly plotted there. And this black line is the plot of the log base 10. And one of the characteristics of a log curve is that it grows very slowly. And so we might use a log curve to mimic or fit to some collection of data. Another type we look at are what are called rational functions. And, rationals are easy to spot because don't these two words rhyme, rational and fractional? So if we have something that looks like, P of x over Q of x, these are called rational functions. So here's a very simple type, sometimes called the reciprocal function. 1 over x is clearly a rational function. Here's a more complicated one, f of x over here on the lower right. Notice this time that we have those dashed lines at 2 and back at -2, and that's because this function is not defined at those two variables, and so we use those dashed lines or asymptotes to help us draw what the function looks like. And it's got these 3 branches or curves. They're distinct, disjoint, and we'll look more at rational functions as we go through the course. In this section, we also talk about algebraic functions, and algebraic functions are constructions that use operations like addition, subtraction, multiplication, taking the powers or roots, and the like. And here are some examples like, a polynomial function with a square root over the top of it. We'd call that, a mix of addition and roots. So this is in that algebraic category. And although g starts out looking like maybe it's a rational function, now we got some stuff added on here, and this best classification we can make is an algebraic. Notice that any rational function is also automatically called an algebraic function. So in that previous screen, down there on the lower right, that function called f of x, we could call it an algebraic function, but we can be even more specific because everything is either in the numerator or the denominator. We can call it rational, as opposed to on this slide, this one called g. It starts off looking like a rational function, but then no, some other stuff is added on. And so we've got the graphs of those, some functions here, some additional possibilities that I just copied right out of the textbook. Take a look. We make mention in this section about trig functions. Here are the big three, sine, cosine, and tangent, and their graphs. They're functions that we use a lot, and you know, they have their own keys on the calculator here, right? Sine, you know, sine of 0 is 0. You see that plotted right there, right? And if we took the cosine of 0, we'd get 1, and we see that plotted right there. And these are the shapes for sine, cosine, and tangent. I hope you're familiar with them. Let's just look at some functions and classify them. That's where the homework starts. And on the top of the screen, I have the questions, and then the answers are right below. So not to cheat, but the first one, we're clearly looking at a function where the x is in the exponent, so we call it exponential, right? It's an exponential function. And that's quite different than the second one, where the constant, the 5 now, is in the numerator, in the where the power goes. This is a quintic or fifth degree polynomial function, but we call it a power function. Can call it a polynomial of degree 5, but more specifically we refer to it as a power function. C is clearly rational. You may call it algebraic, but it could also be considered a rational function. And finally, the last one, we call it a polynomial function, although it does fit that big classification called algebraic. We can be more specific and say it's a polynomial of degree 4, the highest power of the exponent. So the homework begins, I believe it's on page 33. And if you take a look at the homework, it starts off from section 1-2 by asking you to classify, and some of these are very easy, like the first one, of course, is a log function, and then, although we didn't devote a slide to it, b is a root function, the fourth root of x. We'd call that a root function, and look at the list and give it the best answer. C would be a rational function, right? It's a fraction, and anything that's fractional, we call that rational. So you do your best on those, and we'll see you all on Monday. Thanks for your kind attention.